Whew. Okay. Hello, everybody. How is everybody doing today? Okay. So today we'll start on part 2 of this probability theory that we started the last time. The last time we talked about random variables, how to discrete and continuous random variables, if you remember, how to get probabilities of those, right? And expected value and variance of random variables, if you remember the last time. Now we'll continue on with transformations of random variables. This is part 2. Okay, and this should be loosely covered in chapter 7 of the book, just loosely. So actually here it's a lot more detailed in a lecture for you to understand what is happening. Okay, so let me tell you now some stuff. Let's first start. Okay, like this. Okay. So we'll talk about these transformations or functions of random variables and why they're important. You know, it turns out they are important to some extent. Okay. So a transformation, or let's say a function of a random variable, refers to changing a random variable by adding or multiplying a number to it. Okay. I'll add something to the random variable, or I'll multiply it by something, and it's going to transform it. Okay. So adding or multiplying a number effectively adds or multiplies that number to all possible outcomes of the random variable. Right? So the random variable can take the numbers 1 through 6, like in a die roll. I multiply by 2, I multiply the number 1 by 2 by the number 6 by 2, every possible number by 2, in a sense. Okay. Okay. Therefore, the process of transforming a random variable creates a new random variable. Okay, let's keep that in mind. More technically, this adding and multiplying is called a linear transformation. Okay, and this is what we'll stick for now, is this linear transformation, to keep it simple. Okay, in the literature, this is what we'll focus on. There are also other nonlinear transformations that, for example, involve squaring of the random variable or taking the logarithm of the random variable. These are nonlinear. They're not that difficult to study as well, but for now we'll just focus on the linear transformations to keep things simple. Okay. Okay, so watch. This is adding a number to a random variable. Okay, given the random variable x, suppose c is added to it. C is any number like 5, okay, for example. Then a new random variable is created called y. So mathematically, y equals x plus c, like this. Okay. Y has the same distribution as x, but it is shifted c units to the right. Okay. Okay. The number line, if c is greater than 0, and to the left, if c is less than 0. So consider the uniform. For example, this is a uniform distribution that starts at 1 and ends somewhere. I don't know. Maybe it ends at 3, probably. Okay, I don't know. Then, if I transform this random variable x by adding some number c, suppose c is 10, okay, then the new random variable x is going to start at 1 plus c, or 11 in this case, and it's going to end at, again, c is 10, so it's going to end at 3 plus c, and this is 3 at the end. And in this case, it will be something like 13 there. Okay. 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 So the whole idea is that I add this c to every possible number. This is adding a number to a random variable. Okay. So the whole distribution is shifted to the right in this case. Okay. Example of an unfair die roll. Okay, suppose X represents an unfair die roll of a probability 0.5 on 6 and 0.1 on the rest of the outcomes. This is the same problem that we had in the, if you remember, on the questions in the last lecture. Okay, this unfair die roll. Okay, what is the distribution of y if y equals x minus 3? So that means what? The distribution shifts to the left by 3 units. I subtract 3 from all the possible outcomes of the die. So now the 1 becomes a negative 2. The number of the die roll that was 2 before becomes a negative 1. And so forth, and now the 6 becomes a 3. So the whole distribution shifts to the left by 3 units. Okay? So now getting a 3 has a probability of 0.5. Remember, the 3 was the 6 before. It's like the transformed 6 is now become the 3. Okay? And the rest have a probability of 0.1, like this. Okay, so I drew it here. This is the distribution of y, x minus 3. And again, before it was 1 here, right? I started at 1 through 6 before. And now everything shifts to the left by 3 units. So now the 1 has become a negative 2. And the 6 has become a 3. And now the 3 has a probability of 0.5. So the probabilities stay with the numbers, okay, as before. Okay. So again, a transformation by subtracting 3 in this case. Okay. Okay. What about if I multiply a number? I transform the random variable x by multiplying a number. Suppose I multiply c by x. Then a new random variable called y is created, and mathematically y equals c times x. And I call the new random variable y. You can call it any letter. You can call it z if you want, or k, or a, or any letter. You can just make sure you call it a new letter to indicate it's a new random variable. Okay, like this. So y equals c times x. Y has the same look as x, but it has become tighter. Y has become tighter, okay? If a c is between 0 and 1. It becomes looser if c is greater than 1. The transform is flipped on the other side of the y-axis if c is less than 0. Okay? So, what happens if c is equal to 0? Then y will not be anything. Y will be 0 as well. So, in a sense, all probability will be on 0. So it's not going to be a random variable anymore. It will just be a number and it will be 0. Okay. So consider the following example. Consider x to be a uniform random variable like this, from 1 through 4, and let y equals c times x, where c is between 0 and 1. This implies that y is uniform between c and c times 4. Right? I just multiply every possibility times c. So 1 becomes a c, and the 4 becomes a c times 4. Okay? Notice there is also a slight left shift, but there would be no left shift if the starting point is 0. So now in this case, the distribution has shifted to the left a little bit as well in this case. Okay? Again, this is multiplying by a random variable, and we might multiply the continuous random variable. In this case, x is a continuous uniform distribution. Okay, it could have also been the case where I multiplied by the die roll, right? And it could be x times c with a die roll, which again would have done the same thing. Okay, or with a discrete distribution. Okay. Okay, so here's another one. Notice that under continuous uniform random variable, the height also changes. When, in particular, when c is between 0 and 1, the height increases, just so the total area is 1. keep the total area 1. And the height decreases when c is greater than 1. Okay? This is because the area underneath the curve has to sum to 1. Okay? This is not the case with discrete random variables. The probabilities simply carry with changing values. For example, consider x to be the unfair die roll again, and now consider y equals 0.5 times x. This implies all values are halved, and the new distribution looks like the following. Okay, so now the 6 times 0.5, or 6 divided by 2, is the same thing. I divide all numbers by 2 in a sense, by multiplying by 0.5. The 6 becomes a 3. The 5 becomes a 2.5. And the 1 becomes a 0.5. So this is a transformed die roll distribution. I just multiply by 0.5. Okay, and this. Okay. So you can also do, what you can do is called a multiple transformation. Okay, consider z. Z equals x plus 5 divided by 2. Does this equal x divided by 2 plus 2.5? In other words, if I first add a number to x and then divide by 2, does this give me the same distribution as first dividing by x by 2 and then adding 2.5? And the answer is yes. So the order of operations in distributive law holds with the random variables. Okay? Okay. 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 Here is another interesting topic. There are some very powerful rules in this case. Okay. Suppose I'm interested in finding out the mean and the variance of a transformed distribution. Okay. So what do? You can first transform a random variable and then separately compute its mean and variance by using a formula. And we know for discrete distributions, the formulas were in the previous lecture, if you remember. What do you do for the expected value in particular? You just, and the mean in particular, you just sum them up and multiply by the corresponding probabilities, if you remember. Each possible value times the probability, and you sum all those up. And then there's also a formula for the variance. This is for the discrete. And if it's a continuous random variable, it's just right, there's formulas for families of distributions of expected value and variance. So you just look at those. Okay? Okay. You look at the families. Okay, everybody? Okay. And you get the formulas there. However, you don't have to do this. You don't have to, if you know the original distribution, you know the x, the original distribution, okay? And you know its expected value and mean, okay, and you know how you transformed this distribution, okay, you know the transformation formula, then there's mean and variance rules that can spit out the mean and the variance of the transformed distribution, okay? So you can follow some basic rules, but they're powerful. Recall expected value of x, Ex is the expected value of x, and Vx is the variance of x. The standard deviation of x means the standard deviation of x and is the square root of the variance. Okay? For any random variable x, it doesn't matter if it's discrete or continuous, suppose that I know the transformation formula of how I got z, or how I transformed x to get z. Then, expected value of z is simply c times expected value of x plus a. And the variance of z is c squared times the variance of x. Okay? So if I know what c and a are, right? That means I know the transformation formula, and I know the expected value and variance of x. I can get you the expected value and variance of z for any distribution. So this is very powerful, okay? Okay. So I can easily figure out the transform variables z's mean and variance by knowing the original x's mean and variance. Okay? Okay. I'll give you an example here, just so you're in tune of what's happening. Okay? Watch. Do you guys remember this unfair die-row distribution that we talked about last time in the questions? It was from 1 through 6, right? And then the 6 was a probability of 0.5, okay? If you remember, we computed the mean. The mean, if you remember, that we computed was 4.5. 4.5, okay? Now, what is the mean of y? And y is 0.5 times x. Well, I just look at these transformation equations. How did I transform? Now, suppose z is y, okay? It doesn't matter what you call it. So y, c is now 0.5. C is now 0.5. Okay? A is 0. A is 0. Okay? So, what will my expected value of y be? It will be 0.5 times the expected value of x. And the expected value of x is 4.5. 0.5 times 4.5 is exactly 2.25. So guess what? The expected value here should be exactly 2.25. I don't have to, again, use these formulas to compute the expected value of this distribution, okay? Similarly, watch. What will be the variance of y? Again, y is 0.5 times x. That means I square the 0.5 and I multiply times the variance of x. If you remember, the variance of x was like about 3.5. That means before how spread the distribution was, or 3.6, I think. Look at the answers from the previous lecture, okay? What is the variance of this one? Notice how everything has become more compact when I multiply by 0.5. The whole distribution has become just more compact in a sense, okay? And so, if it's more compact, its variance has shrunk. And by how much is the shrinking? By a factor of 0.5 squared. Okay? So, its variance is 0.5 times 0.5, so it's 0.25. So its variance now is 0.25 of the variance before. Okay, before it was much more spread out, so the variance is shrunk by a factor of 4. However, the standard deviation, if you look again, these formulas, I just take the square root of this stuff here. The standard deviation, it's half as much as before. Half as much, because it's 0.5 here. So it's the standard deviation of y is 0.5 times the standard deviation of x. So before, the standard deviation was like 1.8, if you remember. This is the average distance from the mean. So now the standard deviation should be about, the average distance from the mean should be about 1 or 0.9, about 0.9, if you compute it, okay? And again, you can use the formulas to get an exact answer and verify those formulas that they're indeed correct, if you would like, okay? Okay. Okay. Okay, here's something called a nice property of a linear transformation. This is a very neat property, okay? Suppose z is f of x, and f of x is a linear transformation of z. So, for example, z equals a times x plus b. This is a linear transformation here, okay? So f of x is c times x plus a in this case, okay? Like this. Then, probability that x is between a and b is equal to the probability that z is between f of a and f of b. Okay? As a numerical example, suppose that z is x plus 5 divided by 2. Again, this is a linear transformation. Okay? Then that x is between a and b is the probability that z is between a plus 5 over 2 and between b plus 5 over 2. In other words, the probability that x is between two values is the probability that z is between the transformations of the same two values. Okay? This is very powerful. Okay? And it's very useful for computing probabilities when you know the exact probabilities of one distribution, but not the other. So either you know probabilities of z or x, but you don't know the probability of the transformed one. Okay? So what do? You first do a transformation to get it to the one you know. You compute probabilities, and then once you compute probabilities, you know it for the transformed one, for whatever you're interested. Okay? So this is kind of very interesting stuff, and I'll show you how to use this. This is pretty important, okay? And it's pretty important in particular because when you compute the probabilities of a normal distribution, that's why it's important. Okay? Okay? So recall from the previous lecture again. It is difficult to compute probabilities for a normal distribution. Suppose x is normal, a normal distribution with a mean, an average of 5, and so the peak is at 5, and the variance is 16, or the standard deviation of 4. Okay? What is the probability of me getting above a 6? Above a 6. Compute probabilities for normal distribution is hard. A table of probabilities is provided for a special distribution called a standard normal. And formally, it is defined as a normal distribution with a mean of 0 and variance of 1. Okay? So I have a table of a standard normal. A standard normal is like your very basic normal, in a sense, okay? A normal with a mean of 0 and a variance of 1. I want to compute probabilities for a different normal, for a transformed normal, in a sense, okay? So, for a standard normal, the units on the x-axis, the possible z-values, are given as standard deviations from the mean. Remember that, okay? To compute probabilities for x, simply transform into standard normal z, and then compute probabilities for z. By the nice property above, the probabilities for z correspond to those for x. So that is the trick. If I want to compute probabilities for x, I have to transform z. So what is the probability that x is greater than 6, for example? How would you proceed? Okay? And I solve it here. You can follow this. I'm not going to follow it. You can follow it separately. I'm just going to show you how to do it. Okay? And what the basic idea is. Okay? I'm going to show you this from what I know. I'm not going to read the slides. Okay? Because you can read them on your own, obviously, and figure them out. And this is the basic thing I'm saying in the slides, is that I'll show you the following. Okay, I have some distribution here, and this is the standard normal. It has a mean of 0 and a variance of 1. So, and a standard deviation of 1 as well. So there's ones around here. And 68% of the distribution is between this -1 and 1, if you remember here, okay? It looks something like this. And now, the whole idea, okay, is that I'm interested, for example, I know another distribution. I put a 0 here because it's kind of far away from the y-axis. And the distribution has a mean of 5, which is somewhere here, and a variance of 16. And a variance of 16, it might look something like this. Okay? And that means it has a standard deviation of 4, about. Okay? Okay, like this. And here is the number. If it has a standard deviation of 4, the variance is 16. I take the square root of the variance to get the standard deviation. Remember that. So the standard deviation is going to be 4, it's going to be 9 here, and here is going to be 1, like this. And around in the middle here is going to be, again, 0.68 of the distribution here, and again, in between here, it's also going to be 0.68. Okay, probability. So the probability of me getting between, and again, this is, I'll call this Z. Normally this is called Z. This is normal, 0, 1. And again, let's just clarify the problem first, okay? Yes, X is normal, 5/16. Okay? And this is X, and this is a normal distribution with 5 and 16, like this. Okay, everybody? Like this, like this. And that means standard deviation of X is the square root of 16. And it's 4. Okay? Like this. Okay? So everybody good there. Now let's see what the question asks exactly, and I'll show you how to do everything. Okay? The question asks, what is the probability of getting above a 6 on this, from this normal here, 5/16? Okay? So now I'm going to watch here. I'll have somewhere here 6. Okay? And now the question asks, what is the probability of getting above a 6? So this should be the area to the right of 6. Okay? Like this. To the right of 6. This is some area. It's not 0.68. 0.68 is the area between 1 and 9. Okay, so let's scratch that out. I don't know this area here. Okay? Now, another interesting thing is I don't know probabilities on this distribution at all. Okay? But I have probabilities for the distribution here, the normal 0, 1. And here, the 6 on this distribution corresponds to some number here on this distribution. It's a normal 0, 1, and the whole idea is if I can get the probability of this number here, and I'll call it this little z here, this little z, okay? If I can get this probability here on the z distribution, this is going to be the exact same area as this one. So these areas here are going to be exactly the same, okay? Okay. So now the whole idea is to know how I can transform, how this distribution gets transformed into a normal 0, 1. And once I know the transformation formula, I can plug in any number from this x and it will spit out a z. Okay? It turns out that the transformation formula is as simple as this. It's x minus the expected value of x over the standard deviation of x, like this. And let me tell you why. And this is equal to, in this case, first let's see what it's equal to. The expected value of x is 5. Okay? And the standard deviation of x, as I compute it here, and this is given, it's 5 and 16, the standard deviation is 4. Like this. Okay? So that means z, again, this is equal to z. Okay, so let's not forget. Okay, like this. So that means if I want to transform any number here from x into z, I just plug in x here and it spits out a z. Okay? Okay? So in this case, I'll plug in 6 equals x implies, okay, this will be 6 minus 5 over 4, okay, like this, and then it's equal to 1/4, and it's equal to z, like this. So actually the number here, okay, the number here that I'm interested in is exactly 1/4 or 0.25 here, okay? Notice something with this transformation, this is plus minus 1 standard deviation from the mean. So the mean here is 0 on the standard normal. The mean corresponds to 5. Okay? The negative 1 corresponds to a 1, because 1 is plus minus 1 standard deviation on this one, and a plus minus 1 standard deviation is 1 and 9. It's plus minus 4 from 5, okay? So the 1 corresponds to a negative 1, and the 9 corresponds to a 1, if you see. Okay? So you can solve it using a system of equations. You can easily solve what the numbers should be if you want, and I'll show you how to do that in the notes and the PowerPoints. But anyway, let's look at some intuition behind the formula here. What am I doing exactly? Why is this the transformation formula? Well, watch. I want to move the 5, which is my center here, okay? Corresponds to the center, and the 0 corresponds to the center here, okay? Anyways, I want to move the 5 to become a 0. So I need to subtract 5. So when x is 5, I need to subtract 5 from it. Or I need to shift the whole thing to the left by 5 units first, okay? but to shift to the left, I need to subtract every single possible number by 5. And then this 5 will become a 0. Okay? Okay? So this is why first, x minus 5, I subtract from x, each possible x, I subtract a 5. And this is the expected value of x in particular. Okay? And then, what do I need to do? My spread is too high here. Here between, I have from 5 plus minus 4 is my standard deviation. Here the standard deviation is plus minus 1. Plus minus 1. How do I convert plus minus 4? So now the distribution becomes tighter. Plus minus 1. I have to divide by 4. Or in this case, I divide by the standard deviation of x. Okay? So this is how I do it. And this is the transformation formula to transform any normal into a standard normal. Okay, everybody? Like that. Okay. Now, the next step in the process, all I have to do now is I got the number 1/4. Once I do the transformation, I have the transformation formula here. Right? I plug in 6 for x, or this 6 here. It corresponds to exactly 1/4 here, where this is 0.25. Okay? And all I need to do now is look at tables, something called a table, for standard normal. Normal. ST normal. Just look it up on Google. There's all kinds of tables there, if you want. So, and then it depends on how the table is organized and what probabilities the table is giving you exactly, okay? I need to know the area to the right of 0.25 in particular, okay? This area here. Is it going to be 50% or more? No, it's going, because 50% is the area to the left of 0. The other 50% of probability is the area to the right of the 0. So this is going to be about, maybe, I'm guessing, around 40% or so. So the probability is going to be about 0.4, I'm guessing here. For this area is about 0.4. Because the whole thing has to be 1, if you remember, okay? And once I know the area here, bam, this is the same as the area here from this nice property. Okay, so all I do is now just find a table to get me the area to the right of the 0.25. Okay, so you can just Google a table, or I provided a table again in the lecture itself, in the PowerPoints. So let's look at what the table says, and let's try to figure out the table. Okay, the one in the PowerPoints. Okay. Okay. Like this. Okay. See, I have here a standard normal table. Let's see what it gives me, this table. Because a lot of them are kind of tricky. There's a lot of probabilities here. Do you see the picture here? You see the picture, right? It gives me the probability of the shaded region. It gives me probability that z is less than below z. So z here is kind of like my 1/4 or something like this. But it gives me the area to the left. I need the area to the right. Okay? So the area to the right is 1 minus the area to the left. Do you understand this? It's 1 minus the area to the left. Anyways, I will first get the area to the left, because this is what the table is giving me. It's not giving me the area to the right, unfortunately. So let's read. Watch. This is z. Z can be 0. Z can be in the area. So whatever is in the middle here are the areas to the left of z, or the probability that z is less than that value. Okay? probability that the random variable z is less than that value. Okay, so these are the areas to the left, where the shaded region is in here. Okay, so what is here? This is z. Z can be 0.1, can be 0. If z is 0, it can be 0.1, 0.2, 0.3, 0.4. This is not very precise here. The precision is here of z. So if z is 0.100, I look at this one. If it's 0.11, I look at this one. If my z is 0.15, I look at this one. Okay? So if my z is 0.15, the probability to the left is going to be 0.5596, or the area to the left here. Okay? Do you understand this now? Okay. So the precision is on this axis, on these columns. Here is the precision. Here is the basic z. Okay. So what do I want? I want my z to be 0.25 or 1/4, right? So I come down the column here. I see my z as 0.2. You see it here, 0.2. And then the precision is 0.25. And 0.25 is exactly 0.5987. 0.5987. So the probability on the left of 0.25, on the left of 0.25, that area is 0.597. Okay, so probability that I get a z that's bigger than 0.25 is 1 minus 0.5987, which is going to be roughly 0.4. It's going to be around 0.4013. 0.4013. So it's going to be very close to 0.4. The probability of me getting a z that's above 0.25. Okay, does that make sense? Okay, so it's very interesting. So this is the table of the normal here. Okay, and does this make sense? So this means that this one is 1 minus 0.5987. And the area to the left of this, right, the area here, is 0.5987. This is why this is 1 minus that, because the whole thing is 1, right? Okay, and then this is 0.4013. That means this is also 0.4013 by this nice property. Okay, and that is the answer there. Okay, okay, everybody. Oh, okay. On the next few slides, I show you how to read this table. Okay, exactly the same thing that I explained. Okay, now this is one table. You can have other tables. You can have tables. Okay, now let me just tell you this table. Notice it only shows me values for the positive z. What if I'm interested in the values for the negative z? Well, because of symmetry, if I know the positive, then it's the opposite with the negative, because everything is symmetric. This is a symmetric distribution. So you have to think a little bit, okay? There is also tables that show you both for positive and negative. But you'll see, because of symmetry, the negative is 1 minus the positive. So if I just give you the positive, you're able to figure out the negative as well. Right? For example, the probability of the negative z, it's below this, is 1 minus the probability of the positive z, because the area to the left here is the same to the right here. Okay? Does that make sense? Okay. So the area to the left of, let's say this is a negative z here, the area to the left of this negative z is the same as the area to the right of this z. The same because of symmetry. Okay? So that is the trick. There's tables that will give you both values. Okay? Then, on how to read the table. Okay? And now, the lecture is almost over. So, let's get on with the questions and the answers. Okay? Just quickly. Assume, which one is this? Okay, let's just pause the video, take a little break, and then we'll go on with the questions and answers, okay? Okay, everybody, we took a little break. Now it's time to continue, okay? And now we're going to answer some questions. Watch. Questions below. I want to know, what is the distribution of the new random variable? I want to know the location of the new outcome space and PDF. Okay, so what do you do? Well, let's draw it. Suppose x is uniform between 0 and 15. Assume a is x plus 2. So x is uniform between 0 and 15. How is this going to work? Like this. Okay, 0 to 15. Like this. And the PDF is 1/15, because 1/15 times 15, right? The base is 15 times 1/15 is 1. So this has to be 1 here, okay? And then a, so I want to transform a equals x plus 2, like this, okay? And so everything shifts 2 units to the right. That's what it's going to look like this, okay? Like this. This is also going to be 1/15. The height will stay the same because everything has just shifted to the right. What is the mean? The mean is 7.5 here. And here it should be 9.5. The variance stays exactly the same in the standard deviation. The standard deviation here is about how much? The average distance from the mean is about 7.5 divided by 2, about 4, 3.5, 4 is the standard deviation. And you can look at the formula. You guys remember what the formula was? It's 1 minus b minus a squared, squared 12 divided by that. So let's just get out, and this is 12 over 15 squared. This is the variance. And so standard deviation of x, I'm just curious myself here, is the square root of 12 divided by 15. Okay? Is this correct? This doesn't make a lot of sense. It's reversed. It's reversed. Sorry, the formula is, I think, is the opposite. Divided by 12, right? It doesn't make sense, this formula. So it should be 15 divided by the square root of 12. Like this. And the square root of 12, I know the square root of 16 is 4. The square root of 9 is 3. So the square root of 12 is about, let's see, about 3.5. So 15 divided by 3.5 is around 4 times 3. What is it? Around 4. Around 4.1, 4.2, something like this. Okay, so it's about this much. Okay, so this is the standard deviation, about 4. So it makes sense. Okay, and the standard deviation is also about 4 here in this one. Okay, if you're curious about this kind of stuff. Anyway, moving on. Okay, you guys are getting this, right? You're getting this. Okay, guys, I want to I'll let you know something before I forget to tell you. There's going to be a lot of work in this class. This is not your ordinary class because you guys are, unfortunately, you're only taking one statistics course. And we have to fit in a lot of information, unfortunately. But I'm trying to make it as simple as possible with very simple examples, just so you get the concept. Okay, everybody? This is the whole idea here. Just so you understand the concept, okay? Anyways, let's move on. Let's delete this. Okay, like this. And what is the next one? X is between 0 and 15. Assume y is 2 times x. So again, I have between 0 and 15. And y is 2 times x. So y is just a transformation of x, so it's going to be uniform as well. And it's going to be twice as much. So I multiply. Here's a trick. I multiply every possible value here by 2. 0 gets multiplied by 2. Here is 1 or something like that. It gets multiplied by 2. Every single possible value. So that is the trick. Again, I'm going to start at 0 and I'm going to end at 30. Now, okay? And the height is going to be half as much, or 1/30th now, instead of 1/15. Okay? Let's move on. J is uniform between 2 and 15, and B is 2 times J. Okay? This is a little bit more interesting. So it's going to be between 2 and 15, like this. And again, please attempt these on your own first, and then look at the answers that I'm doing. Don't just look at the answers first, please. Okay? Okay. So this between 2 and 15, that means the base is what? 13. So this is 1/13. Okay? This is x. And what does this mean? J is 2 times x, right? Just want to remember here. Wait, B is 2 times J. Okay, so it doesn't matter. Just call this J, and you call this B. Is 2 times J. Okay, B is 2 times J, like this. Okay, so I just multiplied J by 2. So it doesn't matter the letters, J, K, Y, Z. Okay, it doesn't matter. These are just random variables. You have to give them some kind of a name, and the letter, you give them a name with a letter. Okay. Anyways, 2 times J. So guess what? I multiply every single possible value by 2. So what is that going to mean? The whole distribution is going to shift to the right a little bit. So now the 2 becomes a 4. Okay? And it's going to become twice as short. And now the 15 is going to become 30, like this. Okay, and the height here is going to be what? 1 over 26, like this. So what is this uniform then? B is now a uniform, you say, between 4 and 30, like this. Okay, so next one. And I posted the solutions on the next slide, so you can see them, by the way. X is uniform between -2 and 15. B is again 2 times X. Okay, so what is the distribution of B? Again, I'm going to draw this out for you. It's going to look like this. And again, the parameters of the uniform are always the beginning and ending points. It's going to be -2 and 15, like this, okay? Like this. How much is the height, or what is the PDF of this? The height is exactly 1 over 17, the height here, okay? About this. And B is 2 times X. So again, I multiply every single number by 2. And what happens? You just, this is what you do. Every single possible number there, you multiply by 2. So it's going to become -4, okay? And up to 30. Now, okay, like this. So B will be distributed uniform, okay, like this, between -4 and 30. Like this, okay? Now, what is the height here? The height, well, it depends on how long the base is 34 units, so 1 over 34. Notice the height is twice as low as before. It's 117, so now it's like half as low. If I draw it accurately, it should be here, something like this, okay? Okay, moving on. So you guys are getting those. Not that hard, right? Suppose X is normal, 0, 16. B is 2 times X. Okay? So X is normal. Let me just, sorry, my 0, 16. That's right. And B is 2 times X. This. And so when X is this normal here, what are you going to do? What is it going to look like? Let's suppose here, and here is 0. It's going to look something like this. And here's the peak, right? The peak is here. Okay. And then it's going to have plus minus 4 a standard deviation. So it's going to be 4 and -4, like this. Okay. Now B is 2 times X. Then I use just intuitively. This means that, okay, the expected value of B, if you remember the mean and variance rules, is 2 times the expected value of X in this case, okay? Which will equal to 2 times 0 equals 0. So the location, the center is not going to change. It's going to be at 0. What about the variance of X, or the standard deviation of X? Is again going to be 2 times standard deviation of B. Sorry, standard deviation of B is going to be 2 times the standard deviation of X. Just look at the mean and variance rules. Okay, and that's going to be 2 times 4. It's going to be 8. So the whole idea, everything is going to become more spread out and just more just flatter like this, okay? And now here I'm going to have 8 or -8 to 8 like this, okay? So this B is now going to be a normal with a mean of 0 again. The mean is going to be 0, or the center is going to be 0. And the variance is going to be 8 squared, or 64. Like this, okay? Let's move on. Okay. Okay, suppose x is 216 and b is again 2 times x. Okay. So a lot of transformations here, okay? You guys are getting the logic of this, right? We're getting the logic. Okay. So again, it's going to be twice as spread out as before, okay? So lastly, what do we have here? X is a normal, 216, okay, like this, okay? And how is this going to look like? Well, now it's going to have a peak at 2, not at 0, okay? And now, again, it's going to have plus minus 4 standard deviation here, okay? So 4, okay, so it's going to be somewhere here, it's going to be 6, and here is going to be -2, okay? So plus minus 1 standard deviation is going to look like this. And then the next transformation is going to be b equals 2 times x. Okay, so how is this going to get transformed? I multiply every single possible value by 2. That is the idea here, okay? So it's going to be the -2 will become a -4, okay? The 2 will become a 4, and the 6 is going to become a 12. Does that make sense? It's going to look something like this. Okay? And I know now that center is going to be at 4. So I know expected value of b is going to be 4. The standard deviation of b is going to be twice as much as before. So it's going to be 8. 8. Notice the 12 is plus 8. 4 plus 8 is 12, and 4 minus 8 is -4. Okay, like this. And so, in this case, b, and then you can use the mean and variance rules. This is the same thing. If you use the mean and variance rules, this is what you're going to get as well. Okay, b is normal. For and comma, in this case, okay, for a comma there, 64, because 64 is the variance. Okay, this. Okay, so we completed this problem. Moving on to the next one. Again, always feel free to pause the video. If you are not getting stuff, try and figure out the stuff on your own. Okay, I know it's a little bit tricky, and you can ask me any questions during the discussion period. It's okay. Okay. Aha. Watch this. This is a little bit of a tricky problem. Suppose I want to convert a normal that I know is 1525 to a normal that's 2 and 4. what is the conversion formula, and just tell me the conversion formula, in a sense, okay? So this is a little bit tricky. It's a little bit tricky. You have to think, because the first thing you want to do is actually get your variance to match. The variance to match. Let's okay. The first thing you need to do is get the variance to match. So the variance for the standard deviation in the first one is 5, and the standard deviation in the other one is 2. So I have to multiply x. Because if you remember our mean and variance rules, the standard deviation is linear in a sense. You just you don't square it. You just multiply it by whatever it is. Okay. So the first thing to do, I have to multiply. This is what I want. I want some kind of a formula like this. Okay. So k equals c times x. Okay. So what is the c gonna be? I have a gut feeling. The first thing, the variances have to match. Okay. So I think it will be 5 over 2. 5 over 2 times x. Okay. In this case, the variance of k is going to be 5 over 2 times the variance of x, and the variance of x is 25. That's right, that's right. So it should be here 2 over 5. Okay. Like this. Because then the variance of k is 4. Is 4. So the variance of k equals 4 divided by 25 times the variance of x. If you just look, the things get squared there. For the standard deviation, like this, okay? And that equals to the variance of x is going to be 25. Right? Okay, so it makes sense. Okay, guys, just pause the video. I'm just pause the video and trying to figure out this one. So, if you want to just pause the video, try and figure out this on your own, and we're going to proceed. Okay. Let's see here. Okay. So this is correct. Okay. So this is correct because the variance of x is 25. That equals to 4. So everything is good. The variance of k is 4. Right? Okay, so you multiply by 4 over 25. Okay. Yes, so you multiply by 2 over 5. Now, what happens to the mean of x when you multiply it over 2 over 5, okay? So this part is good here. 1 second. And then the expected value of x is 15. Okay, does this make sense? Plus a. Now the expected value here, so I just adjust a to whatever it needs to be in this case, okay? 2 equals 2 over 5. Okay, like this. The value of x is 15 plus a, and then I solve for a. Okay, in this case I solve for c. Okay, so that's going to be 15 divided by 5. See 15 divided by 5 here. It's going to be 3. 3 times 2 is 6. So a is minus 4. And then c is 4. C is 2 over 5. Okay, so this is how I did it. How you're supposed to do it, let's be more formal here. You set up a system of equations. The standard deviation of k equals c times standard deviation of x. And the second equation, so this is equation 1. And the whole goal is to try and figure out the c and the a in this formula. And this is your conversion formula, okay? And then equation 2 is, okay, equation 2 is this one with the expected values. So this is how you do it. I did it a little bit different. I just used my intuition a little bit here, but it's the same thing. Okay, it's the same thing. So you solve for c in terms of the expected value and standard deviations. To get standard deviations, all you take is the square root of 4 and the square root of 25 to get the standard deviations. The variances are just going to be squared, right? So solve for c and a in these two systems of equations. Is that simple? Okay. Okay. And this is what I'm doing here. I solve for a and I solve for c, and what is my last is the full equation. Then it's going to be okay. It's going to be 2 over 5 times x minus 4, like this. I use here the mean and the variance rules to double check, and I use some logic here. It's what I put. Okay. So there's multiple ways you can approach this to get this number. Bam is the correct answer. Okay. Okay. What is this saying? I'll show you what it's saying. I'll show you exactly what it's saying here. You got two normals. You got k and you got n. So k is 2, 4. So if you want to be more precise, k is like a normal, 2, 4. And then x is 15, 25, like this. Okay, so let's just pick out a few numbers, use our transformation. And what is the transformation formula that we got as a solution? So this is kind of a double check to make sure everything is straight and make sure there's no everything straight. Okay, so k is 2 over 5x minus 4. And this is the transformation formula. Okay, That makes sense? Okay. So I'll show you here. What our goal will be to try and transform. Okay. You just draw it if you're not sure. Okay. You put 2 here. Here is going to be 0, the y-axis. And it's going to look something like this. Okay, like this. And then 4 is a variance. So plus minus 2 is the square root of 4 is 2. That is the standard deviation. There's going to be 4 here. And here, the standard deviation again, it should be here. It's 0. So sorry. Okay. So here, from between the 0 and the 4, this should be, again, this is not drawn to scale. It should be symmetric. It should be 0.68 of the distribution. And here, again, I have this axis here. If you have something like 15, okay, and the variance is 25, so square root of 25 is 5. The standard deviation is 5. So for plus minus 5 from the 15 will be 20 and 10, like this, okay? And then this should be also 0.68 between the 10 and the 20. So guess what? The 10 should correspond to a 0. The 15 should correspond to the 2, and the 4 should correspond to the 20. Okay? I'm just double checking here. Okay, so we put for x here, and you can write the formula vice versa, depending on what you want to transform to what. So you can just solve for x in terms of k, or k in terms of x. The formula is exactly the same, right? It doesn't matter. In this case, it's very easy to plug in the x instead of the plug in the k. Okay, so I'll just put, let's put 10, it should spit out the 0 in theory, okay? Okay, that's 2 over 5 times 10 minus 4. Look, this is 10 times 2 is 20, divided by 5 is 4, minus 4 is 0. Bam. Everything is straight. Okay, the 15 should spit out a 2. So you put in 15 there, you get 30 over 5 minus 4. This is 6. It's 2. 2. Bam. Everything is good. And lastly, last but not least, 20, right, should become a 4. It should become a 4. Okay. Then how would you do that one? You're going to put a k here, and it's going to be 2 over 5 times 20. Okay, minus 4. This is 40 over 5 is what? 8. 8 minus 4 is 4. So 20 indeed becomes a 4, right? Okay, so the formula is correct. I'm just double checking with numbers that I know should exist. Okay. Okay. I'm just double checking, so you can double check as well if you're not sure, if you do the math right. Okay. Here's the next problem. So please pause the video, try and do the problem on your own, and then we'll work it together. Okay. So let's go. Okay, so let's start now. How long a tire lasts is given by a normal distribution with a mean of 36.5 1,000 miles, and a standard deviation of 5,000 miles. What is the percentage of tires? What percentage of tires can be expected to last more than 40,000 miles? Okay, so this is, I'll draw again a picture for you here. Like this. So the whole idea now is that there is this company, and this is X tire last miles. So I put miles here. Okay, like this. And different tires will last different amounts of miles. So some will last more than 36,000 miles, some will last less than 36, but on average, most should last around 36,500 miles. This is about the peak, or this is like the highest probability here. It's like 36, and these are in thousands. Like this, okay? And plus minus 5,000 miles is going to be here and here. Okay, so you just know this. Just so it makes sense, everybody, okay? So 68% of the distribution is there. Okay. Like this. 31 and 41. Okay, and 36 is the middle. And now the question asks, sorry. What percentage of tires can be expected to last more than 40,000 miles? So any random tire I get, what will be the percentage that it lasts more than 40,000 miles? Any random tire. So I just pick one, I close my eyes, I pick a tire. How much, what is the percentage chance it's going to last more than 40,000? So I put a 40 here. And I want to know the probability to the right of this one. Okay? Like this. Well, this is a normal distribution here, right? And what is the distribution of this? The distribution of this normal is like X is normal. All right. That's right, correct. Okay, X is normal with a mean of 36.5 thousand miles. I just take off the zeros there to avoid any kind of confusion. And the variance is 25. Okay. 25,000 miles. Right. So the standard deviation is 5,000 miles. Okay. Oh, okay. Okay, like this. And I want to convert this because I don't have a table for this kind of a distribution. Okay. And actually, yes, I don't have a really table. So I need to convert it to a normal 0, 1. This is the next step. Okay, like this. And I need to see this 40. Where is this going to correspond to the normal 0, 1? I know the 41.5 corresponds to a 1 because it's one standard deviation. And the minus 1 corresponds to the 31.5. And the 0 corresponds to the 36.5. So I want to know on the 40, somewhere here, what is this number going to correspond to? I just use the formula. You guys remember the formula? I did z, and this is z here, and this is x. Z is x minus expected value of x over the standard deviation of x. And what is this going to equal to? Z equals to x minus, in this case, 36.5 divided by 5, or 5,000, okay? So 1,000 here, okay, everybody? And then, for x, what do I put? To just clarify, it should be 40, because I'm interested to know, right, 40,000 miles. So I just put the 40 here, okay? It's going to be 40 minus 36.5 over 5. And what is this number equal to? You can just get a little calculator and you'll get it. Okay, it's going to be, yes, it's going to be exactly 0.7. 0.7, okay, is the number here. And so the number here is exactly 0.7. So I'm interested in the normal distribution, the area to the right, and this area and this area are exactly the same. Exactly the same area. And so I just look at a table. That's going to tell me 0.7 and to the right of 0.7. However, the table does not have to the right of the number. It has only to the left of the number, right? So I look at where 0.7 is, and I subtract 1 from it, okay? Right? I just go back to the table here. Like this. And then I see 0.70. So the precision is going to be 0. So it's going to be 0.758. So the area to the left is 0.758. And this area is 1 minus 0.758, right? Is this area. And if you just do the math, it should be 0.242. 0.242. So about a 25% chance I'll get a tire that lasts more than 40,000 miles. So this should also, this area should also be 0.242, right? Or I get again a 24.2% chance I'll get a tire that lasts more than 40,000 miles. Okay? Okay. Okay. What's going on there? Okay. So, again, consider the tire company. This time is distributed normally, about 20,000 miles. And what is this number here? 1,0,0,0,0, a million with a million variants. You know, the square root of a million is like 1,000, right? So standard deviation is about 1,000. Yeah, so 1,000 times 1,000 is a million, right? You know this. And then So the standard deviation is 1,000. What is the probability of a tire lasting 18,000 miles or less? What is the probability of getting between 19,000 and 21,000? Okay. So again, this implies the standard deviation is 1,000. Do this prompt on your own. Try to figure it out. Here I specify the answer. Okay. Okay. And lastly, let me just write a prompt for you that we'll discuss in class. Hello, everybody. Hello, everybody. Again, I'm back. So here's the prompt for the class. You guys remember in the previous lecture, we had the prompt for class also. And it was about the salad and the salad grab and the distribution of the salad grab. And if you remember, the distribution was like a right triangle between 70 and 100 grams. So call this variable x, this random variable of salad grab. Now, suppose, for this, let's say random variable x, now suppose the server gets a spoon this twice as big and serves salad with a bigger spoon. Assume that the distribution of the salad grab with the bigger spoon is z equals 2 times x. What is the PDF of z? What is probability that x is between 90 and 100, and what is the probability that z is between 90 and 100? What is the probability that z is between 180? So let's put this 3, and let's put this 4. 180 and 200. Okay, so these are the questions to answer. Try and answer them on your own. We'll discuss this question in class. Okay? I'll see you on Wednesday.